Hello everyone, I'm Minghan Zhu. I'm happy to present our work, MonoEdge, Monocular 3D Object Detection using Local Perspectives. Let me start with a question. What are the visual cues that we use to perceive the distance in a driving scenario? There are two easy answers. First, size. Farther objects appear smaller in the image. Second, position. Farther objects are located higher in the image, if we assume that we have a typical viewing angle and objects are on the ground. These two cues are widely used in designing networks for monocular 3D perception tasks. However, they are not the whole story. Distance can be perceived without size or position information. As shown here, the two boxes are roughly the same size at the same position in the images. But we can still tell that the left one is farther and the right one is closer, because distance can be perceived from local perspective distortions. Farther objects show weaker distortions and look flatter. Here, the box on the left presents weaker distortion than the box on the right. Overall, the key takeaways are that we can use the local perspective distortions to estimate the distance and yaw of objects, and that we can achieve better monocular 3D object detection by incorporating local perspectives into existing networks. We use key edges and key-edge ratios to parameterize the local perspective distortions. Key edges are the vertical edges of a 3D bounding box projected in an image, denoted as hi. Key-edge ratio Rij is the length ratio between key-edge I and j. From the key-edge ratios, we can derive objects' depth and yaw angle. We need at least two key-edge ratios and the physical length and width of the object. Notice that camera parameters are not needed in these equations. I want to remark that our method enabled the direct estimation of yaw angle from the local appearance of the object. Previously, people mostly regressed the allocentric angle alpha first, and converted it into the yaw angle theta, with the global position of the 3D bounding box center in the image. In contrast, our method directly calculates the yaw angle from the key-edge ratios. To successfully regress the key-edge ratios, there is a trick. We know that RAB is the inverse of RBA. Regressing either of them gives the other. But we choose to always regress the smaller one, because of the better numerical stability. In practice, we always regress the ratio R21, R41, R32, and R34, where 1, 2, 3, 4 are image-based indexes, and 1 is the key edge that is closest to the camera. The ratios are then converted back to the vehicle-based indexes A, B, C, D by the four-way classification of alpha. We conducted experiments on the Kitty and nuisance dataset. We outperformed several strong baseline methods by incorporating the local perspectives. In conclusion, while existing monocular 3D object detection networks mainly exploited position and size information, we propose to leverage the local perspective distortion effect, which is parameterized by key-edge ratios. Our method enabled the direct estimation of yaw angle and improved overall accuracy in monocular 3D object detection. Thanks for listening.